Summary of chapter 3, separation of variables. This is a method which can be summarized in 7 steps. So we identify if the partial differential equation is linear and homogeneous. Right, homogeneous can be easily tested. You just check if 0 is a solution. This most of the time works. If it is linear and homogeneous, then we assume a product form for the solution. So we write u to be a function of t, or a product of t and x of x, two functions. And then we try to separate them. So we sub it into the PDE, and then we get a differential equation for t, and we get a differential equation for x. And doing this, we find a separation constant, which we often call lambda, because one side of the equation only depends on time, the other side only depends on x, and so there must be constant lambda. One of these problems which we find is complete. Complete in the sense that we have the right number of boundary conditions based on the rule of thumb. It's typically the x problem. So then this is something we can solve, and we do solve, and then we find the eigenvalues lambda n and the eigenfunctions xn. We take those lambda n now for the other equation, typically the t equation, and then we solve the t equation for these values of lambda n, and we get tn. So having the tn and the xn, we can combine them, and then the un are written as xn of x, tn of t. These are kind of the elementary solutions, which we then, 6, use the superposition principle to sum them all up. So we write the solution u of x and t as the sum of an, tn of t, xn of x, and an are coefficients, which we just don't know just yet. But in the last step then we use the initial condition to find the coefficients an. And typically this then leads to finding a Fourier series, which we did in the previous chapter. So, 7 steps. If we have non-homogeneous problems, we have to go one step further even. We have to do like an 8-step or a 9-step if you like. So there's 2 strategies. One strategy is we write the solution u of xt as the sum of v of xt plus w of xt. Okay, and then we choose a simple something, and w should be a homogeneous problem. This does not always work, but it works very often. So v is something simple like an ODE, w is a homogeneous problem. Strategy 2 can be used if we have homogeneous boundary conditions, because in this case we can solve the corresponding homogeneous problem and find the eigenvalues and eigenfunctions for the homogenized problem. And then we expand everything in those homogeneous eigenfunctions. Every non-homogeneity is expanded out in a series in these eigenfunctions, and then we can come down to a problem of matching coefficients.